question 24 from chapter 11, asking what is the lowest unoccupied molecular orbital in the pi molecular orbital diagram for 1,3-butadiene. So let's first draw how does 1,3-butadiene look. First, we know it's a butane. 1, 2, 3, 4. Ene, but there's two enes, dienes. It says the first alkane is located at 1. The second alkane is located at 3. So 1, 2, 3. Now, wait. Yeah. This tells us that there are 2 pi bonds and there are 4 pi electrons. Now we have to draw an orbital for each pi electron, so that would be 4 pi electrons in total. 1 pi, 2 pi, 3 pi, 4 pi. And let's fill it up. So we have 4 pi electrons, so 1, 2, 3, 4. We have 2 occupied orbitals and 2 unoccupied orbitals. These will be the anti-bonding. This is our highest occupied molecular orbital, so this is our HOMO. Right? Yeah. And this is our LUMO, the lowest unoccupied molecular orbital. And so starting from 1, that has 0 nodes, but going upward we add 1 to each. So like 2 would have 1, 2, 3 nodes. And a node is just, we have 4 pi electrons, so it'll be 4 nodes in, there'll be 4 p orbitals in total. And a node would just signify whether they have the same spin or not. So 0 nodes means that all of the, wrong thing. 0 nodes means they would all have the same spin, the same side. Meanwhile, 1 node would mean like half of them would have the same spin and the other half would have a different spin, compared to 2 nodes where they just divided up for them to be in like opposing spins if they're in separate nodes. But our node that we have is 1 node, so it'll be like the one that I drew earlier, where we have 1 node in the middle and then 2 nodes spinning in the same direction here, the other 2 nodes spinning in the opposite direction. So let's start from A. We can see that this one has 2 nodes, not what we're looking for. This one has 0 nodes. This one has 1, 2, 3 nodes. And this one has 1 node. We're looking for 1 node. So D is our answer. The second question I got is question 14 from chapter 12, asking to rank the compounds from the slowest to fastest reactivity towards electrophilic aromatic substitution. So we have to look at what's connected to them to see like how fast. Is it a strong activator, a weak activator, maybe a deactivator? So let's look at 4 first. This is a methyl on it. It's a weak activator. It would do para and ortho, but we don't care about like where they'd go. We're just looking at strength for now. And then this carboxylic acid is a strong activator, so this will have dominance over all. This will be the fastest reaction. And then, wait a minute. Yeah, so this one will be the fastest. Meanwhile, bromine is a weak deactivator, and then there's no activator here. Alright, so it's saying from slowest to fastest, meaning that the slowest will have the highest amount. So we know that carboxylic acid is the fastest, so anything that doesn't have 3 in the beginning is wrong, so we can cross out A. Now let's compare this weak deactivator and this weak activator. Because bromine has a super strong inductive effect, meanwhile methane doesn't really do much. It lets things happen slowly. It doesn't really push for things to happen. Bromine would have a higher priority. So bromine would be in second place. Which only C is our option. And then, so we could cross out both of these. And so let's see, why is 1 stronger than 4 even though like there's nothing speeding up the process? It's most likely due to a hindrance. There's nothing, anything could react with this benzene ring compared to this phenyl, where it would have to like be careful of the methyl even though it's not pushing for a reaction to occur. So that's why C is our answer.